more definitions. So this time we're looking at a planar graph. A planar graph is basically one that has no edges that intersect. So they don't cross over. The only place they can intersect really is at the vertices. So if you have a look here, we've got two edges that are crossing over. That is not planar. Whereas here, in this one, nothing crosses over. Yes, we have some intersections, but they are only at the vertices. Quite often, we're asked to make graphs planar. We don't like working with non-planar graphs. What we need to keep in mind when we're doing this is that what vertices originally connected, well, they must also connect in the planar graph. So in this example here, that's exactly what we're going to do. Now keep in mind there are many different versions. So let's have a go at a couple here. What I usually do is start with my vertices. So there's my four vertices, A, B, C and D. Now A and D always connected, B and C always connected. I could have D to B. Okay, now the only one that I'm missing there is A to C. They don't have to be straight lines, so I could go like that, and now I've got a planar graph. Let's do another one. So I'm going to start with A, B, C and D. And I'll still connect B to C and A to D. I don't have to, but I have. This time I'm going to leave the connection between A and C there. And obviously I still need to have this connection between D and B. I just don't want it to cross over. So I could go that way. And that is planar form for this network. Is there another? Yep, there are many. And I can move the vertices around. Don't think that you can't do that. So this time I could do A and move C up there, move B down there and D there. Now I need to make sure that A connects to D, which it does. I need to make sure that B connects to C, which it does. I need to make sure that A connects to C, so I'll do a straight line there. And I need to make sure that D connects to B. And there's that line there. So that is also planar form for that graph up there. And there are many more. A face of a graph is a region in our graph. So it's the amount of regions that it's divided up into. Something that we need to be really mindful of here is that the region outside the graph is also considered to be a face of the graph. So in this particular case, you do have F1, F2, F3, F being the face, and you have F4 outside. That's something to keep in mind when we're using Euler's formula, which is the next section here. So Euler discovered that for connected planar graphs, there is a relationship between the number of vertices, the number of edges, and the number of faces. And there's our rule. V minus E plus F is equal to 2. Euler's formula. Euler was a German mathematician who did a lot of work in this area. Let's have a look at how we use Euler's formula. So first of all, what do we need to do here? Consider the connected planar graph. Now remember, connected, I can get to every vertice from every other vertice without lifting my pen. Planar, I don't have any intersecting edges, so that's why it's a connected planar graph. So part A wants us to write down the number of vertices, the number of edges, and the number of faces. So let's do that. How many vertices are there? Pretty simple there. Number of vertices is equal to 4. A, B, C, and D. The number of edges, let's count them. 1, 2, 3, 4, 5, 6. So the number of edges is equal to 6. What else do we need to find? The number of faces. 1, 2, 3. Don't forget that one outside. So the number of faces is 4. Part B wants us to verify Euler's formula. Now remember what Euler's formula was? V minus E plus F is equal to 2. And this verify is a very important word in that question. Verify means that you need to prove, basically. So this is the way you should set out these questions when you are asked to verify. So let's say this bit of the equal sign over here is going to be the left-hand side of the equation, and this bit here is the right-hand side. So I'm going to start with the left-hand side, and it's V minus E plus F. I'm going to substitute in my values. So I've got 4 minus 6 plus 4. And what do I get when I work that out? I get 4 minus 6 is minus 2, plus 4 is positive 2. And now I'm going to look at the right-hand side of the equation. And the right-hand side of the equation is equal to 2. So you can see there that our left-hand side is equal to our right-hand side. And therefore, Euler's formula has been verified. Looking at the next question, a connected planar graph has 4 vertices and 5 edges. Find the number of faces. There are a couple of ways I could do that. I could imagine what the actual graph looks like. So it's got 4 vertices and 5 edges. Well, I've just drawn a planar graph with 4 vertices, A, B, C and D, and it's got 5 edges. How many faces are there? 1, 2, 3. Therefore, 3 faces. What other way could I have done that? Well, let's use Euler's formula. So what do we know here? So we know that V, the amount of vertices, is 4. We know that the amount of edges is equal to 5. And we know that we are looking for the amount of faces. So the rule was V minus E plus F is equal to 2. So V is 4, E is 5, F is what we're looking for, and that equals 2. 4 take away 5 is -1. And bring that over the other side, and it becomes +1, and so we get 3 faces. So we're getting exactly the same answer. One method uses the diagram or the graph, and the other uses Euler's formula. Both are correct, and both would be acceptable in a test.